So today we're going to talk about the conversion between context-free grammar to push-down automata. So we talked before about, so far we've had like or NFA, which these two are equivalent to each other, and the language they describe are the regular expressions. So these three are all equivalent to each other, and then we introduce a context-free grammar, which we know is a broader class than the regular expressions. There are some languages that can be expressed with a context-free grammar that cannot be expressed with a regular expression, whereas everything that can be expressed as a regular expression can also be expressed as a context-free grammar. So if you have like regular expressions, then context-free grammar is a bigger class. Now, regular expressions is equivalent to what you can get from the DFA and the NFA. And we introduced another automata, which is the push-down automata, which is essentially an NFA that also has a stack, where it can push things into the stack and pop from the stack. And what it pops from the stack can help make the decision on which state to go. And so a PDA can do everything that an NFA can do. Like if you just think about it, it's very obvious, because whatever you have in an NFA, you can have in a PDA. So if you have an NFA, you can just be like, oh, this is an NFA. Well, I can just treat it like a push-down automata, except it doesn't use a stack. So a PDA can use a stack, it doesn't have to use a stack. If it doesn't use a stack, it's basically just an NFA. But because it has a stack, it can do more things with the stack. So a PDA can do more things than what you can do with the NFA. And we also showed the standard language of 0 to the n, 1 to the n. That's something that cannot be done with DFA and NFA, but that could be done with PDA. So the interesting thing is PDA is actually equivalent to the context-free grammar. So everything you can do with a context-free grammar, all the languages you can describe with a context-free grammar, can be implemented with a PDA. As in, you can build a PDA that recognizes exactly that language. And also the other way around. If you have a given PDA, you can convert it into a context-free grammar. So there's two sides to the proof, right? There's given the PDA, what is the context-free grammar? Or derive a context-free grammar from it, convert from PDA to CFG, and given a CFG, construct a PDA for it. We are not going to be covering both directions, actually, mainly because the PDA to CFG it's really complicated, and it does a lot of things, and it's also very mindless as well. Like you're creating a variable for like every little thing, and you create a whole bunch of variables, and you have a giant context-free grammar at the end. And we're not going to get into that. It's a lot of work, and it's not a very meaningful exercise to actually go through, except the knowledge that they are. What is more practical is the conversion from CFG to PDA, and that's what we'll be doing here. So you are given a context-free grammar, and from that context-free grammar we want to build the PDA. And I would actually argue that this is probably simpler than regular expression to NFA, but I don't know. That one is also a very simple conversion, so that's kind of debatable. So let's see how it works. Let's actually look at an example. So let's look at this example of a context-free grammar. So we have this context-free grammar. A goes to 0, A1. A goes to B, and then B goes to the hashtag. So this accepts languages of the form a bunch of zeros followed by a hashtag followed by a bunch of ones, where the number of ones is the same as the number of zeros. So for example, let's say we look at the string where your input string is 0, 0, hashtag 1, 1. This is part of the language of the context-free grammar. So when we string should give us yes. So how it works is, well, we look at it this way. The top variable in our context tree grammar, that's a start variable. Which means every input has to have the form of either 0A1 or the form of B. Okay, so they wrote it in 2 lines, but you can actually just put it in 1 line simply. Don't get confused about how many rules it has. So it has 2 rules. So A has 2 rules, either 0A1 or just B. So every single string that is accepted that is recognized, that is part of the CFG, has to have the form of either 0A1 or B. So if it has the form of 0A1, so if we're looking at it as having the form of 0A1, we can match this 0 with this 0. Right? So we can match this 0 with this 0. But then here we have another A. Well, A is a variable. We can produce either 0A1 or B. So from this A, we can try to produce 0A1. So instead of A over here, we're going to have another 0A1. And then we still have that one at the end from before. Now this 0 can match with this 0. But now we have hashtag here, we have an A here. So this A, we can see, can we produce something that leads to the hashtag? Well, we can produce A, we can produce a B. So we replace this A with a B, but then that B we replace with the hashtag. And so we replace the B with the hashtag. And now we can match this hashtag with that hashtag. We match this one with that one. We match this one with that one. So what I did was basically, this is basically just looking at a context tree grammar. It's kind of like deriving the production rules in reverse of sorts. But what we did here is we matched up with our input with some intermediate form of our context of how it's supposed to look based on the context tree grammar. So initially you just have A, but then A can produce one of these, so you can transform A into 0A1 or B. And now your target becomes to match with 0A1. And then you produce A again, and then your target becomes to match with a 0A1 again. So this target is something that we can actually implement using the stack. So in a PDA, our stack should indicate what is our current target. And based on that, we will match up our input with the elements of the stack. That's our target. So ideally what we want actually is, initially our stack, so let's say we have a stack. Let's push the bottom first, because we should always start by pushing the bottom so we know when the stack is empty or not. Okay, so we're going to push the bottom first. And then we look at, okay, so what is our target? Our string should look like which variable? So initially, based on the context tree grammar, it should always begin with the start variable, which is A. So the entire string has to have the form, has to be something that can be produced by A. So our stack should actually have that A. We need to match our input, the entire input, with A. Now, of course, A is a variable. It doesn't have terminals. So when we want to match with a variable, we need to replace A with something that it produces. So we need to perform a production rule on A and produce something. Now, what can we produce from A? From A, we can produce either 0A1 or B. Using this example, we actually want to produce 0A1 first. So from this A, we should produce 0A1. What we do is we take out that A. If we see a variable, we take out that A and we replace it with one of its production rules into the stack. So we remove the A and instead we put in the production rules. So we can put in either 0A1 or B. And in this case, we're going to put in 0A1 because for this particular choice, 0A1 is the correct choice for this string. When we put in 0A1, we actually have to be a little bit careful because What is it that needs to match first in 0A1? Is it the 0 or the 1? 0. The 0 needs to match first, right? 0 needs to match first. But when we push into the stack, what do we see first after we put stuff into the stack? 1. We will see the 1, well, we will see whatever's in the top of the stack, right? So if we just pushed in 0A1 like this, we don't get to see the 0 or the A. We only get to see the 1. The first thing we pop is the 1, the first thing we need to match is the 1. 0 first, we don't want to match with the 1. So instead what we do is, we push in reverse. Okay, so variable is replaced by production rule in reverse. This is probably the main point for this whole conversion. So instead of pushing 0A1, we will push 1A0. Okay? So this is our stack. And then in our PDA, we need to read the 0, so we match with that 0, and so we can remove the 0, we can pop that 0, but then we see another A. What do we do with this A? We do the same thing we did before. Whenever you see a variable, whenever you see a variable in stack, so this is in the stack. So whenever you see a variable in the stack, you can replace it with the production rule. That means you put it into the stack, but in reverse order. So again, you have this A, well, let's replace it with 1A0 again, so you put it in reverse. So actually, let's look at it in a longer way. What we really want is, we have some input, 0, 0, hashtag 1, 1. And I'm not going to draw the PDA yet, because PDA is a little big. But what we ideally want is, we have the stack, we push the bottom as usual, and then we also push the start variable, because the input has to be something produced by the start variable. So what we're going to do is, we try to match the input with the top of our stack. If the top of our stack is a terminal. If the top of our stack is a variable instead, we don't do any matching yet, but we replace that with the production rule in reverse. Right? We replace the variable with the production rule in reverse. So we see an A, okay, we will pop the A. Oh, wait, no, I should have done that. Let's just cross that normally. We pop the A, and instead we push 0A1 in reverse. So we actually push the 1 first, then we push the A, then we push the 0. Okay? Now we try to see, okay, what's in the top of our stack? It's 0, which is a terminal, which means it has to match. We need a 0 and we need a 0. Now, what's in the top of our stack? It's an A. When it's an A, we do the same thing. We replace it with the production rule. So we pop that A and we put in the production rule, which is 1A0. That old 1 from the previous production rule, that's still there, because we need to deal with this A before we look at that 1. So we need to deal with this A before we look at that 1. So this 1 stays there, but on top of that you have another 1A0. So 0 on the top, then A, and then 1. And now we try to match again. So this is a terminal. Can we match? 0 and 0, they do match. But now we see an A. When you see the A, again we need to replace it with the production rule. Here, instead of replacing it with 0A1, because our next target is hashtag, we should actually replace it with the B. So we pop the A, push the B, B in reverse, but it's just one symbol, so B in reverse is just B. And then we have the B at the top. And again, this is a variable, so we replace it with the production rule. The only production rule for B is hashtag, so we replace it with the hashtag in reverse, which is just the hashtag. And now we can match hashtag with hashtag. Let's match these two. And then what do we have at the top of our stack? 1. Let's match. And then we have 1 as well. And we can still match. And then we have the bottom. So when you have the bottom and your input is done, that should mean you're done, the string. So that's how the PDA is going to look. All right. So a very simplified version of this PDA is like this. So it's showing with only 3 states. The actual PDA will have much more than 3 states, of course. But essentially it's saying, okay, you start with some initial state. Initially you push in bottom and A, where A is the start variable. So you push them into Q1. And then from Q1, it's showing this as a very simple loop. It's not going to be such a simple loop, but basically it's going to check. Well, if the top of my stack is a 0, and my input is 0, I can match them. I can do the match of 0 with 0. If I can match 0 and 2, I just match them. I don't actually do anything else. I don't push anything to the stack. I just remove a 0 from the stack, and I read a 0 from the input. So I match the input to the stack, whether it's a 0 that's matching, or a 1 that's matching, or it's the hashtag that's matching. But if the top of my stack is not a terminal, if it's not a 0 or a 1 or a hashtag, then it's a variable, either A or B. So if it's A, I can replace it with the production rule of A in reverse. And it can be anything. It can be 1 A0, or I can replace it with B. Whenever I see an A, I actually have 2 choices, but this is fine because the PDA is not deterministic, right? So just like an NFA, you could have multiple choices, and that's fine. One of those choices should hopefully lead to acceptance. It doesn't matter what the other choices do. So we'll actually have 2 different transitions, either replace A with 1A0 or replace A with B. And if we see a B, we can replace B with the hashtag that's. Any questions about this very simple model of the PDA? Okay. Now, this is basically how the PDA looks. The only slight issue is that this PDA is actually pushing multiple things at a time, which you're not supposed to do. You're supposed to push, each transition is supposed to be read something, pop something, and push something else. But pushing multiple things is actually not that big of a deal, because what we can do is, if we want to push multiple things at once, we can just do something like this. So if you want to push, say, B, C, and D, what we can just do is, okay, we push B, go to a state, and then in this state you have no choice but to push the C, and from this state you have no choice but to push the D. So in order to go from Q0 to Q1, you have to push the B and C and D. So you just basically make states in the middle to put in the rest. Once just means go through a bunch of states where you push in the next symbol one by one until you reach the target. So how does this actually look like in practice? The slides here unfortunately don't really show a detailed example. It does show like this big arrow without really clarifying how that looks. So I actually prepared a separate set of slides. The CFGtoPDA example, it should already be uploaded in the classroom, where basically it goes through the whole process and it shows the complete PDA. So basically the idea is you first draw the base model, which is these 3 states. It actually becomes 4 states. You can see you're pushing 2 things. It actually becomes 4 states. You draw the base PDA, and then you just draw all of these arrows. All of these production rule arrows, you just keep drawing them until you're done. So this is how the base PDA will look. So we're going to start with some initial state. We need to push in. Let's just, I'm going to make it a bit simpler and just write the words instead. So we push the bottom, we go to some state. From this state, we also then need to push the start variable. So let's use the example here. So here, it's a different example. Actually, no, let's use this one. We can use this example so that you have a different example in the slides that you can check out later if you want. So we push the start variable, which in this case is A. to some state. So now in our stack, we will have the bottom and A, right? This was the initial state of our stack. So if at any time, so from this state, if at any time we see a terminal at the top of the stack, we try to match it with the input. So if we see a 0, we match it with that 0. If we see a 1, we match it with the 1. If we see a hashtag, we match it with the hashtag. So all of those can just be simple self loops. So we can just have a self loop where you can read and pop 0. So your stack must have 0 and your input must have 0. They must match. So if they match, if your input has a 0 and your stack also has a 0, you can just match them all. Or you can read 1 and pop 1. Or you can read the hashtag and pop the hashtag. Okay, so you'll have 3 possible transitions for matching the terminals. And then, if everything is matched, you should go to the end, which is just popping the bottom, and that goes to the accepting state. Okay, so these are separate. Let me just put some indicator. All of this is for that transition. Okay, so this is the base PDA. You're always going to push the bottom, and then you're going to push the start variable. And then you'll try to match all of the terminals. So whenever you can match the terminals, you match them. Match between the input and the stack. So read 0, pop 0, or read 1, pop 1. And if you have more symbols in the alphabet, like the hashtag, read hashtag, pop hashtag. Okay? And then after you're done with reading everything, including the variables, which we didn't draw yet, but then you can, when you can pop the bottom, you go to the accepting state. So now what happens if you see a variable? Well, that's the second step is going to be to add a new state for each variable. So each time you see a variable, you need to pop that variable and replace it with a production. Right? So popping the variable, we need to go to some state. So we have a state where, so here we have 2 variables, A and B. So we will have a state that pops A, and we will have a state that pops B. Okay, so we have a state that pops A. Just for space, I will probably write that a little closer. Okay, pop A and pop B. So for each variable, you make a new state to pop that variable, because in case you find that variable in your stack, you should remove that. And then from this state, you need to add the production rules, which is the final step, where we will add production rules. We add transitions for each production rule. So if you're going to pop A, what are the possible production rules? So we have 2 choices. We can either push in 0A1 in reverse, or B in reverse. So we're going to do both of them because this is not deterministic. So if we want to push 0A1, we have to do it in reverse. So you actually push the 1 first, then the A, and then the 0. So from the state, you can push. We can push 1, go to some state. And then we go back here where we push 0. So you always go back to this center state. So this center state, the third state from the top, this state is where all of the stuff happens. It has the matching between the terminals and the input, and then when it sees a variable, from here, it replaces that variable with the production rule, and you go back to the state where you can start matching again after you finish replacing it. So if you see an A, you can remove the A and replace it with 1A0, which is this production rule in reverse. Or if you see an A, another option is you can replace it with the B instead, in reverse, which is just B. And this one only needs 1 arrow, so you can just directly do that and call it push B. What about for B? For B, we have one more production rule, which is the hashtag. So if you see a B, you can pop the B, and then you push the hashtag back inside. Push the hashtag. And this will be your final PDA. There's nothing else left. So if this is your PDA, let's take a look at this PDA and try to match the same input that we had before. Okay, so if we have, what's going to happen? So we have, the input is 0, 0, hashtag 1, 1, and then we have a stack. So we start at Q0. So I'm not actually going to state because there's a lot of states. Also, by the way, for your final exam, which there should be a question on CFGtoPDA in your final exam, you're not required to name any of the states. And I'm going to do that for all questions. Even when you need to run an NFA or a DFA, you can leave the state names blank, as long as, you know, if it's a circle or it looks like a state, it's a state. The names are not really important. Well, maybe for the intersection of DFAs, having names on the states will help you, but I don't care whether you put it or not. But it's better to put the names. For CFGtoPDA, there is no point in putting the names of the states because there's a lot of states. So initially we're in Q0. We push in the bottom, and we come here. And now we push A, we go to the center, which is where all the looping happens. I think it's usually called the Q loop. Q loop. From here, what can we do now? So what's the top of our stack? It's an A. Because it's an A, the only option is to actually pop the A and come here. So we will pop the A and move to this state. From this state, we have two choices. We can either use the B production rule or we can use the 1A0 production rule. So based on what this looks like, we can imagine that we would actually need 1A0. We know what the result is, but generally both of these will be valid, and non-deterministically it will choose both and one of them will be correct. So we will push the 1 and come here, we push the A and come here, and then we push the 0 and go back to the center. Now here we can match the input 0 with the top of the stack 0. So we read 0, pop 0, that first one there, read 0, pop 0. Now our top is A. So we can pop A again, we come over here, and now we push in another production rule, and we will do the same one, 1A0 again. So we push 1, push A, push 0. Now again, we can match 0 with 0. So we read 0, pop 0. Again, the top of our stack is A. So we pop A. This time from this state, we will actually be using the B rule this time. So we will push B. But this is another variable. The top of our stack is variable. So we pop the B, and there's only one choice here. We push the hashtag. Push the hashtag. And now from the hashtag, we match hashtag with hashtag. So we read hashtag, pop hashtag, read hashtag, pop hashtag, and then we next the 1. So again, we can match. Read 1, pop 1, read 1, pop 1. Next top of the stack is also a 1. We again read 1, pop 1, read 1, pop 1. Now the top of our stack is the bottom. So we can pop the bottom and get to the accepting state. And when we're in the accepting state, if the input is finished, then the answer is yes. So this will be accepted. Any questions so far on how this works? So here's another example that we can go through. I won't need to draw anything because I already have the slides here. So we have a simple graph, two variables, S and A. S produces AS1, S0 will produce 1, 0. A can produce either S0 or it can produce epsilon. So we only have three simple steps. You draw the top 4 states first, and that's always going to be fixed. It's not going to change. and then we draw a state for each variable that we pop, and then the third step is we draw paths for all of the rules, each of the rules one by one. Okay, so this is going to be your base PDA. It's always going to be the same. It's not going to change. You're going to push the bottom and then push S. Actually, it's different here because here the start variable is A, and our alphabet had a hashtag as well. But in your final exam, that's not going to be S, and your alphabet will be binary. So you don't need to worry about hashtags. You don't need to worry about a different start variable. You can just push S over here, and then you only have these two transitions for matching. 0 matches with 0, 1 matches with 1. So 0 in input matches with 0 in the stack, 1 in the input matches with 1 in the stack. So you're just going to have these two transitions, and then when you're done matching everything, you pop the bottom and you go to the ascending state. Okay, so always start with this base PDA of 4 states with these arrows. That's step 1. And then step 2 is you add a new state for each variable. So the variables we have here are S and A. So we add a state to pop S, and we add a state to pop A. So we have an S, we add a state that just pops S and does nothing. And then for A, we add a state that just pops A and does nothing else. The final step, which is also the longest step, is the production rule. So for each production rule, we need to draw a path, which could just be one arrow or it could be multiple arrows depending on how long it is. But we need a path from that variable to Q. Okay? And it has to be, the path has to read the production rule in reverse order. Okay, so it has to be in reverse order. So the first rule we have here is AS1. So S produces AS1. So from S, we need to draw a path of pushing the 1 and then pushing the S and then pushing the A. And going back to the 2. So AS1 in reverse is 1SA. So we start with the 1. We push the 1 into some new state. We push the S into a new state. And then we have A, we push the A, and we go back to Q. I mean, you can also just push the new state and epsilon to Q loop, but there's not much point in that. So the Q loop, because we need to go from S back to Q loop, but we need to go there in a path that pushes in 1SA, the entire production rule in reverse. And we do this for all production rules. So the next production rule we have is 1, 0, and this is produced by S as well. So from S, we need to push 0 and then push 1. So we see the 0, we push the 0 to QS3, and then we push a 1 to Q. And then the next rule we have here is S0, which is produced from A. So starting from A, you can push the 0 and then push the S and then back to the Q loop. Finally, we have epsilon, and actually for epsilon you don't need to push anything, right? Because epsilon is not a variable or a terminal. I mean, it basically is an empty string, right? So from QA you can just go straight back to Q loop without as an epsilon transition. And this will be your final PDA. Any questions? So I know this looks really vague and complicated. I'm not going to give you a giant context-free grammar. In fact, there will be, so this one has only 4 production rules. In your final exam, it will also have maximum 4 production rules, not more than that. Actually, maybe I might reduce it to 3 because 4 is probably still a lot. So maybe maximum 3 production rules in your context-free grammar, and you just draw all those errors. If this notation is complicated, because you might notice there's a lot of epsilons in all of these transitions, you can just use this notation instead, which is perfectly fine. So you have your base is always push bottom, push S, pop bottom, and then the self loop is read 0, pop 0, read 1, pop 1. So everything from above this will be the same. And this arrow, that will not change. And then for each variable, we have pop S, pop A into 2 different states. And then for each of those, you have a sequence of pushing the entire production loop in reverse. So for AS1, you have push 1, push S, push A. And then for 1, 0, you have push 0, push 1. And then for S0 from A, you will have push 0, push S. And for epsilon, it's just epsilon. Alright, so this notation might be more convenient for some of you. So if it's okay if you use this notation instead, because for most of the arrows, only one thing is happening, right? This is the only arrow where two things are happening. It's read and pop, and this is a very simple arrow. It's always read 0, pop 0, read 1, pop 1. For all the other arrows, it's either only a push happening or only a pop happening. So you can draw it like this. All right, that's kind of all that I had here. Does anyone have any questions? Should I go to another example of converting, or is this good? Another example. Okay. Let's come up with another example. Actually, which notation would you prefer? Should I use the words, or should I use the triple of words? Okay, let's go with the words. Let's make up a context-free grammar. Anyone have any suggestions? So S can produce something. What should it produce? It could be anything really. It's just, do we have any nice examples here? Probably. Actually, no. If we're going to see nice examples, we might have them. We could do our classic arithmetic expression. Maybe a simpler version of the arithmetic expression, like this. I like the brackets. Actually, yeah, let's do this. Let's do the brackets. Alright, is there a binary example? A good binary example? This is one example we can do. So it only has two rules, but it's pretty straightforward. It's 0, S1, or epsilon. Okay? So we start with the base.
So add another variable.
Add another variable? Okay. Let's say instead of going to epsilon, it goes to A. So I don't want to add too many new variables. So let's say, and then A can go to what? Let's say A can go to either 0, 1, or it goes to 1, 0. I don't know. So, yeah. So essentially, we'll have like the middle is going to be either some mix of 0, 1, 1, 0, or 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, or 0, 1, 0, 1. And then on the left side, you have a bunch of zeros, and the right side, you have a bunch of ones that match. Okay, so it looks a bit weird, but it's an example of context-free grammar. Regardless, it's a context-free grammar, that's what matters. We could also recursively put an S here, but I don't think that's going to matter much. So from this initial state, you push bottom, go to the state where you will read 0, pop 0, read 1, pop 1, and then the final state from popping the bottom. Okay, so this is the base, which never changes. By the way, I think I mentioned it earlier. In your final exam, you are allowed one A4 sheet of paper where you can write whatever you want in it and take it to the exam. So if you want, you can draw this base, so you don't need to memorize this base. You can just draw this base, it's always going to be the same. You can probably also draw a complete example just so you know how variables match and production rules, but at least the base will probably be helpful. But yeah, so we start with this base, that's always going to be there, and then what are the variables we have? We have S and A as our variables, so we can add the two variable states. So this one is top S, this one is top A. Okay, that takes care of the variable zone. Now from each of these states, actually rather, for each production rule, we need to draw the paths from the state to back to the loop in the center. So for 0S1, the path is going to be 1, push S, push 0. So we're going to go from S, we're going to push 1, state, push S to a state, and push 0, you can go straight back. Push 0. The other rule is AA, so we can just push A, and then push A and go there. Alright, so we're done with the AA. Then you have, actually 0, 1, 1 is probably another good example now that I think about it. Sure, let's go. So for 0, 1, we actually push 1 first and then we push the 0. So from here, we push 1 over here and then we, let me, just in anticipation for the space, I'm going to write it like this. Push 1 to this state, from this state, you go there and you push 0. That takes care of the 0, 1 rule. We also have a 1, 0 rule where we push the 0 first and then we push the 1. So let's push the 0 to this state and then push 1. Alright, does that make sense? So this is going to be the final PDA. One thing you could do, so not in this example, but sometimes you might be able to actually reuse some of these production states if the suffix matches. So what I mean is, let's say we have a case where, actually I can just do an example, like let's say S goes to either 0S1 or it can go to 1S1. Actually, no, this. Alright, let's say 1S01. Okay? So here's another example of a context-free grammar with 3 rules. We can do the same thing. Is it okay if I erase this? Okay, let's reuse the same base. One thing we could do is, so there's only one variable, so you just pop the S, and you go here. Now from here, we have 3 rules. So the first rule here is 0S1. So I'm just going to do it like this. So we push the 1 to this state, and from here we push the S, and then from here we push the 0. Okay, so popping S, so for this first rule is 0S1, so we're writing in reverse, which is 1S0. So we push 1, push S, push 0, and back to the loop. Now, for this second rule, which is S goes to 1S01, you need to start by pushing 1 and then 0 and then S and then 1. So you need to start by pushing the 1. If you need to start by pushing the 1, one thing you can do is you can add a new state. Or you can reuse the previous push 1, because that one already has a push 1. We already have a state for pushing the 1. So if it overlaps, there's no need to make a new state. You can go, this is your push 1, but then after that you need to push 0. So now you can't reuse this push S, even though there is an S there, that doesn't matter. The next, after the 1, immediately we need to push 0. So from here, we need to draw a new state for the 0. So now from here, we can diverge to the state where we push. After that, we need to push the S, push S, and then after the S, we need to push 1, and that's the end. So that goes back here, push 1. And then the final rule here is just epsilon. So epsilon is just epsilon. You can just put the arrow directly back and just call it epsilon. So epsilon doesn't have push or pop or read, and it's just epsilon, which means you can just go there with nothing actually happening except the change of state. All right, so any questions about this? So yeah, in your final exam there will be a context-free grammar with maximum 3 rules, and you just need to draw this PDA for it. So it's pretty simple. You have a fixed base, draw the states for each variable, and then for each production rule, draw the path from that state to back to this cube. Okay, and you do that for all of the rules, and you're done. That's it. And there'll be at most 3 rules, so it shouldn't be too much. And it's probably not easier than the reversing a regular expression. That's probably still the easiest question, but this might be the next easiest, probably. Or I guess regular expression to NFA might be easier than this as well. And then CFGtoPDA. And then probably the intersection of DFAs. I think that's also straightforward, but that one might take some time. And then Chomsky normal form. Actually, Chomsky normal form is also good. I think in general, the final exam is probably going to be really easy because I was advised to make the final exam easier. Final exam questions to be easier than the quiz questions, because quiz question is like one quiz. You can prepare for just one question, and I'm only counting the best 4 out of 5 as well. Whereas final exam is like you're going in preparing for 5 questions. Those 5 questions easier than the quiz questions. I mean, I don't think the quizzes are hard either, but hopefully the final exam should be fine. Okay, any last questions? All right, so I guess that's it for today. Don't forget that you do have a quiz next class.